For those who are new, this series uses www.falstad.com for circuit simulations. Hello everyone, welcome to the inductor episode of our Falstad simulation series. Today we'll explore how inductors work and see their behavior directly in the simulation. Let's get started. Inductors store energy in a magnetic field and resist sudden changes in current. They are widely used in power supplies, filters, and signal processing circuits. Simply put, inductors help smooth the current flow and reduce noise in electronic systems. In this circuit, we're using a DC voltage source, inductor, and resistor connected in series. The resistor limits the current, while the inductor stores energy in its magnetic field as the current increases over time. When we start the simulation, the current doesn't instantly jump to its maximum value. Instead, it gradually increases as the inductor builds up its magnetic field. This delay is what makes inductors special. They resist sudden changes in current. First, we calculate the time constant of the circuit, which tells us how quickly the current rises in an RL charging circuit. The time constant, often denoted by tau. The formula is tau equals L divided by R. Here, L is the inductance in henries, and R is the resistance in ohms. First, we calculate the time constant, tau, which is equal to L divided by R. Here, L is 3 henries and R is 140 ohms. So tau equals 3 divided by 140, which is approximately 21.4 milliseconds. This means that after 1 tau, the current reaches about 63% of its maximum value. 2 tau, the inductor is roughly 86.5% charged. At t equals 3 tau, it's about 95%. At t equals 4 tau, about 98%. And at t equals 5 tau, about 99.3%. After 5 tau, the circuit is practically fully charged. The current in a series RL circuit during charging can be calculated using the formula. The current at any time t is given by I of t equals I max multiplied by 1 minus e to the power of negative t divided by tau. Here, I max is the maximum current determined by the voltage source and the resistor. T is the time elapsed, and tau is the time constant. As time increases, the current gradually approaches its maximum value, following an exponential curve. Step-by-step current calculations. Maximum current, 35.71 milliampere. Current at 1 tau, 22.57 milliampere. Current at 2 tau, 30.86 milliampere. Current at 3 tau, 33.92 milliampere. Current at 4 tau, 35.05 milliampere. Current at 5 tau, 35.45 milliampere. The voltage across the inductor in a series RL circuit during charging can be calculated using the formula. V of t equals V multiplied by e to the power of negative t divided by tau. Here, you already know that V is the supply voltage applied to the RL circuit, t is the time elapsed, and tau is the time constant. At the moment the circuit is connected, the inductor initially takes the full supply voltage, and as time increases, the inductor voltage decreases exponentially toward zero. Step-by-step inductor voltage calculations. Initial voltage is 5 volt. At 1 tau voltage is 1.84 volt. At 2 tau voltage is 0.68 volt. At 3 tau voltage is 0.25 volt. At 4 tau voltage is 0.0915 volt. At 5 tau voltage is 0.0335 volt. Short explanation. At the start, the inductor opposes the sudden change in current, so it takes almost the full supply voltage. As time goes on, the inductor voltage falls rapidly and approaches zero because the current becomes steady and no more change occurs inside the inductor. When the switch is changed, the inductor begins to discharge. In this stage, the 140 ohm resistor is involved in the circuit and causes the current to decrease gradually over time. During the discharge process, the inductor is no longer receiving energy from the source. Instead, it releases the stored energy from its magnetic field. The current through the inductor decays exponentially. The current is given by formula. Here I0 is the current just before switching. The voltage across the inductor during discharge formula is like that. Why is the voltage negative? During the discharge process, the inductor tries to maintain the current flow. Instead of opposing the rise of current like in the charging phase, it now opposes the decrease of current. To keep the current flowing in the same direction, the inductor generates a voltage of opposite polarity. This opposite polarity is represented by the negative sign in the formula. If you would like to challenge yourself, you can try changing the values of the inductor, resistors, and the power supply to perform new calculations and observe how the circuit behavior changes. Thank you for watching. If you enjoyed the video, don't forget to like and subscribe. See you in the next video. Bye.